All right. Good morning, afternoon, or good night. I'm not exactly sure when you're watching this, but I am going to attempt to teach this lesson from the comfort of my home. I'm going to be writing over the PowerPoint and then going from slide to slide. We are going over chapter 16, part 1, which is halogen alkanes. We're going to be working on organic part 2, and the goal is to finish organic part 2 the 2 weeks we come back from spring break. So what I think I would like to do is record these lessons and then meet up with all of you on Google Hangouts a couple of times a week to answer specific questions that you may have. All right, so you can pause the video at any time to solve a question, and then I will go ahead and solve it. So if you want to try to solve it yourself, go ahead and pause the video now. Otherwise, I am going to go ahead and solve the question. So the bell work is what always applies to a nucleophile. So if you remember from organic part 1, a nucleophile is a lover of the nucleus. And what we know about the nucleus is that it is positive in nature. So therefore, the identity of a nucleophile is that it would be negative in nature. And that doesn't necessarily mean it has to have a negative charge. Extra electrons means that it could have a negative charge, but it definitely has a lone pair of electrons, because the idea is that pair of electrons will reach out to grab an electrophile. So a nucleophile is a lover of the nucleus, and an electrophile, just to remind you, is a lover of electrons. So electrophiles tend to be positive in nature, or missing a pair of electrons. They have the ability to receive a pair of electrons. So it's actually very similar to acid-base theory, but instead of giving and taking away hydrogens, we're giving and taking away electrons. And so the learning objectives, and yes, you will have to explain learning objectives. A lot of this unit is very picturesque. I think text messages might come in and show on the screen, unsure. So maybe I will have to figure out how to turn that off. But learning objectives. Learning objective 16.1, recall the chemistry of halogen alkanes in the following ways. Hydrolysis, formation of nitriles, formation of primary amines by reaction with ammonia. And then interpret the different reactivities of halogen alkanes with particular reference to hydrolysis and the relative strengths of their C-halogen bonds. So, halogen alkanes. First of all, what do they look like? A halogen alkane is when you have any alkane connected to a fluorine, a chlorine, a bromine, or an iodine. So these can be very simple molecules, but they could also be more complex in nature. When we're talking about substitution reactions, we're talking about substituting one element for another element in general, or one group of elements for another group of elements. So once again, halogen alkanes, as you can see, they are just halogens attached to alkanes. Alkanes, if you remember, are hydrocarbons with single bonds only. There is a general formula. You do not have to memorize it. However, and I would suggest not memorizing it, just for the fact that sometimes you have single halogen alkanes, sometimes there's two halogens on there. And so this formula would change for the amount of groups that you would add to the molecule. The type of reaction. So this is the major thing you need to pick up from today's lesson, which is a nucleophilic substitution reaction. And so a nucleophilic substitution reaction is basically replacing one nucleophile for another. So replacing one nucleophile for another. And so you're going to have an initial molecule. And this is going to be called your reagent or reactant. And you are going to have another molecule. The original organic molecule, this one, has what's called your leaving group. In this case, your leaving group is iodine. And the other molecule, the CN-, is your attacking group. And so the idea is that the attacking group would love nothing more but to take the place of the other group that's on the molecule. So the idea is that if the attacking group is stronger than the leaving group, the attacking group will assume the leaving group's place. Just like a regular single replacement reaction, to be honest. You do not have to memorize the strengths, the relative strengths of attacking groups and leaving groups. However, it does make sense that iodine would leave for the fact that iodine is a weak boy, like some of you have said. So this reaction would happen. There's actually a mistake in this product now that I'm observing it. In this product, when you show the connection in the bonds, you should actually show the carbon attaching because it is being attached at the carbon. And so I am going to walk you through some nucleophilic substitution reactions, and we are then going to go on to the mechanism today. So what are the nucleophilic substitution reactions? The first type is with alkali, which is strong base. So you might see it in questions as NaOH, KOH, but it's really just the OH- that is reacting. The rest of it is a spectator ion. So spectator ions, remember, are not generally mentioned, but they are part of the compound. So the general reaction is that you have your halogen here, you have your attacking group there, and the attacking group kicks the halogen out and assumes its place. And that's how you turn a halogen alkane into an alcohol. So note that the OH- is a nucleophile in this reaction, and also that the Br- is a nucleophile. It's just that the OH- is stronger than the Br-. It is important to note that the reaction conditions is heat under reflux. That is the condition for this reaction. And the refluxing mechanism, I'll see if I can post a video of it, but it allows you to heat without evaporating volatile organic compounds so that they would stay at such a, it's kind of like a Goldilocks temperature where the molecule is heated enough to do the reaction, but you will not lose your molecule to the outward atmosphere. But you do need to know for substitution reactions, heat under reflux is the essential condition, so make sure to include that in your learning objective assignments. For halogen bond strengths, you can use silver nitrate to test the rate of the reaction, which is something that we've actually just looked at in this past unit. And the reason why we can use AgNO3 to test the rate of reaction is because when we have a halogen alkane, if we were to form silver bromide, silver iodide, or silver chloride, we would produce a colored solid. It turns out that the fastest nucleophilic substitution reactions take place with iodine, and the slowest ones take place with fluorine. And this has to do with their relative bond strengths, which you can pick up from the bond energies or just from remembering from last unit. Bond length equates to bond strength. So the idea is the following. So let's say that you had this reaction. then you had this reaction. Let's, instead of fluorine, can I erase? Let's do chlorine. In both of these reactions, you are going to produce a halide ion. A halide ion. And so if you wanted to predict which of these reactions would happen first, if you were to add silver nitrate into your mix, as your halide is being made, it would start to react, or it would start to precipitate with the Ag plus that is present. So this would make AgBr solid, and this would make AgCl solid. And so the idea is that you can predict the relative rate of reaction. The question is, which of these two bonds do you think is easier to break? Take a moment to think about that. The CCl bond should be stronger than the CBr bond due to the fact that bromine is a larger atom. So you would notice that this bond would be the one to break first, which means you would form AgBr first, so this would be the faster reaction, and this would be the slower reaction. Believe it or not, when comparing bromine and chlorine, chlorine is usually used in most labs because, albeit it is a slower reaction, it actually produces a greater yield of product, meaning that although the reaction is slower, it is more thorough in terms of making the right product. All right, the next thing is hydrolysis. So the hydrolysis reaction is also a nucleophilic substitution, but your nucleophile is water. Water is not a great nucleophile because, at least not in comparison to hydroxide, because although it does have the pair of electrons, OH minus easily can attach, whereas water has to actually, once it attaches, it has to release a hydrogen afterwards as a result. But this reaction does happen, and the swap out that happens is the following, which is the bromine and the OH swap out. So it's actually the same exact products almost as the last reaction, except you do end up with the extra H+, which would be strong acid. Do note, this reaction takes place slower than the reaction of OH minus, like I said. Okay. This is a list of the bond energies. It helps to further explain. This bond is weaker, so it'll be a faster reaction. So I'll allow you to answer the checkup questions. I already did sort of answer them in the explanation. What I'll be doing is I'll mainly be walking you through the mechanisms, and I'll be walking you through the Cambridge questions. The second type of substitution is with cyanide. So the cyanide molecule actually looks like this. I'll draw it out now. It is C with N, and then you have a triple bond, and then you have a pair of electrons here, and you have a pair of electrons here. And it turns out that the negative charge itself is actually carried on the carbon. And the reason why the negative charge is carried on the carbon is because carbon in the Lewis structure has 1, 2, 3, 4, 5 electrons that it has ownership of, and nitrogen also has 1, 2, 3, 4, 5 electrons that it has ownership of. And so the idea is that carbon has one more than it should. It does meet its octet like it needs to, but it's carrying the extra electron in the process, and so it carries the negative charge. So that is important when we get to the mechanism and the mechanisms with cyanide, because it is always these electrons that are the ones attaching to the molecule, which is why you see in this reaction you are swapping out simply the bromine for the cyanide, but notice that it is the carbon that is attached to the other carbon in your product. You do need to know conditions for this reaction, which is cyanide, and that would be the spectator ion, so it doesn't matter what that is. It could be KCN, NaCN, whatever. And ethanol, which is a type of alcohol, and then heat under reflux as well. You'll notice that a lot of times the condition for most of these organic reactions are heat under reflux, especially the nucleophilic substitutions. This is a great reaction for organic chemists, because one of the things that organic chemists need to do is they need to start from simple starting materials, and they have to actually build to molecules such as drugs. And so, like, if you want to be a pharmacist, you would start with simple materials and then you build up to larger molecules. So this is one way that you can add extra carbon atoms to your carbon chain. And so this, for example, goes from ethane to propane. And so that is a unique aspect about this reaction. So if you need to add an extra carbon, this is one way to do so. So then the reaction with NH3 is similar to the reaction with water in that NH3 doesn't have a negative charge, and also it's going to have to get rid of a hydrogen in the process. So your nucleophile here is NH3. It is a weak nucleophile, but it's a nucleophile, and it will kick bromine out. So bromine gets kicked out and NH3 goes in. But when NH3 goes in, it does have to drop a hydrogen. And the reason why, if you draw it out, is the following. You would have CH3, CH2, N has a lone pair of electrons, H2. This already satisfies the octet rule, and there is no spot for an extra hydrogen. So that extra hydrogen does need to go to the side along with the bromine that got kicked out, which is why it is a product of HBr. Again, it can be written as H plus Br minus, or it can be written as HBr, because this actually is a strong acid. I don't believe it's on the list you need to memorize, but it is. So one thing to note here is that if you do not have excess ammonia, because people bought it all out due to this coronavirus, you could get a mixture of products, because what can happen is the amine that you produce can attack another halogen alkane instead of staying in the ammonia solution, and it can produce a secondary amine instead. So basically this could attack another halogen alkane and then just link together, basically. All right, so pause the video and see if you can figure out which of these are classified as nucleophilic substitutions. Okay, so did you get it right? Number 1 is a nucleophilic substitution. Number 2 is a nucleophilic substitution. And number 3 is a nucleophilic substitution. And every single one of these, you are swapping one nucleophile for another. So then, why can ammonia and amine act as a nucleophile? Real quick. Because they both have a lone pair of electrons. All right, so that was the first half of the lesson. You should probably pause now, give yourself a little bit of a break, and then move on to part 2 when you're ready. Part 2 is the mechanism. So the mechanism of nucleophilic substitution. Remember, with mechanisms, we are telling a story of what happens, what bonds break, what new bonds are formed, and in what order does this all happen. So looking at the same reactions, we are going to now look at the mechanism of nucleophilic substitution. And this is one of the major things that you would need to know in any Organic 1 class in college. All right, so let's take a look through the learning objectives. It says candidates should be able to describe the SN1 and SN2 mechanisms of nucleophilic substitution, including the inductive effects of alkyl groups. I always think of inductive effects as with a little help from my friends. Friends being the carbons that are around. And the learning objective 16.1c is to recall that primary halogen alkanes tend to react via the SN2 mechanism, tertiary halogen alkanes via the SN1 mechanism, and secondary halogen alkanes by a mixture of the two. You're probably like, what language is this? And I get it. When I took chemistry, this was one of the most confusing concepts when I first learned it, but I will try to make it as simple as possible. And so we're going to start with talking about what does SN1 and SN2 mean, and then we will talk about when each type of mechanism happens. Remember that on the Cambridge exam, you could be given one of a bunch of different mechanisms, so you do need to go ahead and memorize all of them. The first one is called free radical substitution. The second one is called electrophilic addition. The third one, or the third and fourth, are the nucleophilic substitutions. There's 2 of them, which we'll discuss very shortly. And the final one is called nucleophilic addition, which I do believe we cover in the final chapter. I am writing out things as I go along like normal because I would like you to track along. All right, so bell work. Take a look at this mechanism. Look at the curly arrows, look at the charges, and I want you to think about what statements about this mechanism you believe are correct. Go ahead and pause the video for a moment and answer it on your own, and then when you're ready to hear, turn the video back on. All right, here we go. So, which statements about this mechanism are correct? Is CN minus an electrophile? Well, that means it would have to love electrons. And if it loves electrons, that means that it would have to be positive. Well, CN minus is not positive, so no. The next one, it is an addition reaction. So an addition reaction means that I am adding something new into the molecule that wasn't there before. And I'm not kicking out any molecule as a result. Because if I was kicking out a molecule, that would be called something else. It would be called substitution. So let's trace to see what happens. In this reaction, notice that cyanide is being added in. This double bond becomes a pair of electrons on the oxygen, which then reaches out to grab a hydrogen. So both cyanide is added into this molecule, and then hydrogen is added into this molecule as well. Nothing has been kicked out because this was not part of the molecule, what's on the side. So yes, it is an addition reaction. And finally, is heterolytic bond breaking involved? So if you forgot what heterolytic bond breaking is, just to remind you, it is a general regular breaking bonds. So it would look like this. Both electrons go to one element and the other element is now deficient those electrons, so you would see a positive and a negative charge. This is happening here, so that is true. So the answer here is statements 2 and 3. So what is the other one if heterolytic bond breaking is just normal bond breaking? If you'll recall, the other type was called homolytic bond breaking. And in homolytic bond breaking, you have the half arrows and production of free radicals. So please do be aware of that. All right, mechanism of nucleophilic substitution. Things you should remember. Nucleophiles, they donate electrons. And the mechanism that's going to happen depends on the structure of your initial organic compound, your initial halogen alkane. And so you'll have a different scenario if it is a primary halogen alkane versus a secondary halogen alkane versus a tertiary halogen alkane. Do you remember what a primary halogen alkane looks like? So it is when you have a halogen connected to a carbon that is only connected to one other carbon. Whereas a tertiary alkane would be a halogen alkane that is connected to 3 other carbon groups, hence called tertiary. Okay, so SN2 reactions. The first thing you need to note is that this happens only with primary halogen alkanes, and that is extremely important. So this was always confusing to me when I was first learning the material, because usually when we memorize acronyms, they connect to something, they have some sort of meaning, and primary typically means first, and so the fact that it's called SN2 does make it a little bit confusing. So here's what the letters and numbers mean. The S means substitution. The N means nucleophile, so why not NS? Unsure. And the 2 means the rate of the reaction depends on the starting concentration of 2 reactants, or both reactants. So the 2 is not the type of reactant you have. It's that the rate of reaction depends on the concentration of both of your reactants. And so when telling a mechanism, it is sort of like telling a story. So here is the story. You have a halogen alkane here. And the halogen alkane has a weak bond between carbon and bromine. The OH is strong enough to attack, and so it does. And so the first step is that your nucleophile attacks. And what happens is this nucleophile attaches into your carbon and almost automatically kicks out your nucleophile. However, note that for a split second in time, you have something called a transition state. Notice that it's represented by dotted lines, meaning that this is showing that for a split second in time that both nucleophiles are attached. But as we all know, carbon cannot have 5 bonds. 1, 2, 3, 4, 5. It would break the octet rule. And so bromine has to get out and leave. And so you end up with your final substituted product. This is actually the easiest mechanism of all of the mechanisms in the class, and it will only be worth 2 points on the Cambridge exam if you were to be given a question about it. So let's take a look at a Cambridge question. It says, when phenacyl chloride is reacted with aqueous NaOH, the substitution reaction follows an SN2 mechanism. So which structure would represent the species formed during the reaction? Notice that they're looking for the transition state. So although you don't typically have to write the transition state, unless asked, you should know what it looks like. Let's take a look again. What do you think is true? You can pause the video. All right, so here we go. Remember, a nucleophile is coming in and a nucleophile is going out. The carbon in the middle should have a positive charge, not either the leaving group or the attacking group. So the answer here would be C. If you got C, you got it right. All right, so now let's see if we can trace through the mechanism ourselves and see if we can get the points. Remember, it says show the mechanism using appropriate curly arrows for the hydrolysis of 1-chloropropane by alkali. Now, alkali does mean OH minus when they say alkali. You do not have to write the spectator. So I'm going to go ahead and write it displayed. However, you don't have to. You could just write it in structural form or in skeletal form. The initial is written to you in structural form. So here we go, plus OH minus. So first of all, you're going to want to draw out the electrons on the oxygen because that is what's connecting. And technically the negative charge is on the oxygen, just to be clear. And so what we do have to write in order to achieve the points are the following. Number 1, we need to write dipoles. If you forgot what dipoles were, they're partial positive, partial negative charges. And so the dipole is right here. And that's just me telling you it's right there because I don't know how to erase yet. So the dipole is right there. And so I have to say that the carbon is partially positive and the chlorine is partially negative. So that would earn me 1 point. The second point is for using my appropriate curly arrows and therefore writing the appropriate product. And so what I want to do is I want to show the curly arrow going from the 2 electrons on an oxygen and joining up because oxygen is going to connect to the carbon. So I want my arrow to go there. And then I want to show that, hey, these 2 electrons are going to break off because carbon has too many bonds if this oxygen connects. So then this has got to go back to the chlorine, which will retain its full negative charge. And so my resulting product would be C, H, H. Everything else gets written the same. C, H, H, C, H, H. And instead of the chlorine, I draw OH, and I draw the Cl on the side with the negative charge. I don't have to circle it, I just do that. It's just a force of habit. All right, see if you can try to solve this one first, and then I will go ahead and I will solve it out for you. All right, here we go. So give the full name of the mechanism for the reaction between sodium hydroxide and bromoethane. So the full name of the mechanism is just nucleophilic substitution. And you do not have to say whether it's 1 or 2. But it is SN2. And I should actually make a note before moving forward. So what do we mean by both reactants matter? So the concentration of both reactants matter because if we go back here, if I increase the concentration of OH minus, then I will have more attacking groups, ha 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 ha, and they will invade our poor little halogen alkane. So we know that the concentration of the OH minus totally matters. Also, if I increase my concentration of my halogen alkane, they'll be more available for my nucleophile to attack, ha 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 ha. And therefore, increasing either of my two reactants will increase the rate of the reaction, which is why, once again, it is called SN2, because both reactants increase the rate of the reaction. The rate is dependent on both. That's me trying to click forward. Okay. So then complete the diagram below to represent this mechanism. Include all necessary curly arrows, partial charges, and lone pairs. So point number 1, partial positive, partial negative. Point number 2, bye. Points achieved. All right, for SN1. The condition required is a tertiary halogen alkane. So for an SN1 mechanism, your halogen alkane needs to look like this. And so this is a substitution that's nucleophilic, and the rate of reaction depends only on the halogen alkane. It does not depend on the nucleophile. And let's try to get an understanding of why. All right, here we go. So, turns out in this mechanism, because carbon has a little help from his friends, carbon, carbon, and carbon, this molecule is stable enough to exist on its own, meaning that a tertiary carbocation can be stable, not very stable, but more stable than secondary or primary carbocations, so it can be pretty stable on its own. Therefore, the first step in the mechanism for SN1 is that your leaving group actually leaves first. So it doesn't matter how much of your reactant there are, because this bromine ain't leaving until it feels like leaving, is the idea. And so the leaving group leaves first. And so only the rate of the reaction is dependent on this reactant, which is why we call it SN1. And so what happens as a result is a carbocation is formed. And then after the carbocation is fully formed, the nucleophile sees there's space available. There's like a spot to put my electrons in, and it's going to happen. And so that's what happens here. So the nucleophile attacks in order to form a new product. So let's take a look at a Cambridge question and go over the mechanism in detail with this Cambridge question and see if we can earn those points. So first one is to give the IUPAC name for the compound. And so to review naming, the first thing I would do is I would draw the whole entire thing out. Sorry guys, I would draw it out. So I'm going to draw out in whatever space I have C, CH2, CH3, because that's what C2H5 is, CH3, CH2, just writing it backwards, CH2, CH3, and then bromine. Then I'm going to count how many can I get in a row. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It looks like no matter how I slice it, this is going to be a pentane. Right? So 1, 2, 3, 4, 5. And then on carbon 3, I notice I've got this and I've got this. So it is 3 ethyl, or 3, it's got to be one line, 3 bromo, 3 ethyl pentane would be the correct name. And so then once we get that point that we pick up for naming, we would then do the mechanism. And so the mechanism, once again, has to be done step by step. I note that this is a tertiary halogen alkane because this carbon is surrounded by other carbons. And so the first step, I still need to write a dipole. So this would be partial positive and this would be partial negative. The first step is that the leaving group happens to leave on its own because the rest of the molecule is stable enough to be by itself. I think I wrote an extra carbon here. Yeah. And CH2, CH3. And so then I have this. And so then I have, that's gone. I have this. And then I have plus Br minus. Let me see if I can erase. I'll figure it out. Erase? Hey, yes, it works. Okay. Unfortunately, we don't get to erase on Cambridge exams because we have to write in pen. All right, let me rewrite this out. So this would be CH3, CH2, C, CH2, CH3, CH2, CH3, and then this is a positive charge. The bromine's on the side. You don't have to write it. And then I'm reacting it with this, so I also have this. And so the idea is that both of these are competing, the Br minus and the OH minus, for who gets to connect with the carbon. And as you saw, the alcohol is more powerful than the bromine, which is why I said you don't even have to write it. I just write it on the side for good measure. And so I'm going to show these electrons coming in for my second point to connect the OH with the carbon. So how do I earn my points? 1 point is earned by writing the dipoles on the initial along with the initial curly arrow going out. The second point is earned for the carbocation. And the third point is earned for the OH going in to the carbocation with the curly arrow and making your final product, which is what I'm writing now. And so, points earned. Type of mechanism, nucleophilic substitution. Now I want you to notice something. This was 1 point. Same question was just asked in the last Cambridge question for 2 points. So full name means they're giving 1 point to each. Over here, you only get 1 point for both parts of the name. So it just depends on how evil they want to be, once again, when creating the questions. So last thing to talk about is the stability of the carbocation. So an SN1 reaction simply can't happen with primary alkanes because a primary carbocation is not stable at all. There are no groups around that carbon to help stabilize. It's missing electrons. Hydrogens are very small atoms, so they don't carry the burden very well, is the idea. So the tertiary carbocation being the most stable is because of the inductive effects of the carbons that are surrounding that carbon. What they do is they donate electrons. So it makes, they don't officially donate electrons, but it's sort of like the electron cloud moves in towards the carbon, meaning that that carbon, as a result, feels more stable because it's feeling the electrons from the other carbons. And so the secondary carbocation falls in the middle, kind of like Goldilocks again. And so although an SN1 reaction can happen with secondary carbocations, an SN2 can happen as well. And therefore, secondary carbocations are usually not tested for that reason. For that reason, they'll give you clearly either tertiary or primary, and you'll know that this happens via the SN2 mechanism, and you'll know that this happens via the SN1 mechanism. And so this checkup is just to draw the structure displayed formula of 2-chloro-2-methylbutane. I'll leave that to you to do. Is it primary, is it secondary, or is it tertiary? I'll leave that for you. And so let's trace through this mechanism one more time. If you want to try to solve it on your own first, go ahead and feel free. Otherwise, I am going to start writing it out. I do like to do this in the displayed format, but if you prefer to do it in the structural format, feel free. Actually, I think I'll show this with the structural just because I showed the last with displayed, so you can see what it looks like. Wait, what did I do? I did the last one structural, so this one will be displayed, so that you can choose. So 2-chloro-2-methylbutane. 2-chloro-2-methyl. Butane. Alkali means OH minus. So first step, because this is tertiary, this carbon is stabilized from a lot of help from his friends. So the first step is to write your dipoles, like always, and then to show the chlorine, just leave. And then you would have CH3, C plus, CH2, CH3. I ended up doing it structural anyways. It's just easier to me, actually. Displayed is easier to see the bonds breaking and bonds being formed, but with structural, it's just easier to write. It takes less room. So then, I don't have to write the chlorine anymore, but you can if you like. What is important though is you have that OH minus in that's ready to attack. And then you end up with your product. And your byproduct, which is the Cl minus. So I thought about it when I was making this one. You haven't seen any with NH3. So what would it look like if you had NH3 as your nucleophile? Let's say that you had Cl, same reaction, but let's say that you had NH3. So this, right? So first step, once again, is the same. You write your dipoles. Chlorine's more electronegative, that's why it's negative. And so you end up with CH3, C positive, CH2, CH3, CH3. And then you have your nucleophile, which is the N. You can write it however you want, but you do need to show that the pair of electrons is on the nitrogen. And so you need to show that this pair of electrons is coming in and connecting, which means that you would have CH3, C, CH3, CH2, CH3. And at this point, you actually have N, H, H, H. So what would happen? because this is a positive right now. It's like ammonium. Well, you still have your bystander. Your bystander was Cl that got kicked out. So Cl minus is still there. And what Cl minus is going to do is it'll grab one of those hydrogens. And so it is a little bit more complicated when you have NH3 or when you have water. So I wanted to show that. All right, so this is the final question for this lesson. And yeah, I know this is a little bit of a doozy for a first lesson because I included not only the reactions and the mechanisms, I'll summarize it at the end, but see if you can solve this, and I'll solve it in just a little while. Once again, pause the video. All right, so how would I solve it? Aqueous sodium hydroxide, OH minus, another way of saying it, reacts with 1 bromopropane to give propanol. And so they ask, how does the first step in the mechanism be described? First of all, we have to figure out, is this SN1 or SN2? And then we have to memorize both mechanisms. So 1 bromopropane, we need to look at that to tell me what the mechanism is. This is 1 bromopropane. Well, no help from my friends because there's only 1 carbon directly attached to this carbon. So the bromine will not be able to leave on its own, meaning that the other group will have to come in first and kick out the bromine. And so that means this is an SN2 reaction. And because this is an SN2 reaction, the first step is going to be the following. You have your OH minus, and that is going to go for the carbon, and the bromine is going to leave. So the first thing would be this. It's A. Lone pair on the OH minus to the partially positive carbon on the 1 bromopropane. Notice B says from carbon to OH, but we always go from the electrons to the electron deficient area or the positive charge. The idea is that the electrons are reaching out to make the chemical bond between the 2 elements, which is why we always show the arrows going from the electrons to the part that has the positive charge, because it's donating electrons too. So that is important. All right, so that is today's lesson. Hopefully you picked up on it. Just to briefly go back over what we went over the different types of reactions. Pretty much just nucleophilic substitution. We went over what happens when I have a halogen with OH minus, when I have it with NH3, when I have it with CN minus, when I have it with water, and how each of these will all replace the halogen. And then we went over the different types of mechanisms. And so you will have an assignment that goes along with this lesson. And I hope you have an excellent spring break. I will be available for any questions you may have, and we will definitely have more sessions together that are live so that I can answer questions and help you with anything that you need help with. Have an awesome day and take care.